Hello, back to algorithm strategy class with me, Giovanni. We will continue our talk about greedy. So, in the last video, we have already talked about these 4 points, and now in this video, we will talk about knapsack problems. There are two knapsack problems. There are 0-1 knapsack problems and also fractorial knapsack problems. So first, we will talk about 0-1 knapsack problem. So the problem is we have a knapsack that has a maximum capacity of K, and also we have an object. And every object has a weight property and also a profit property. Now, if each object cannot be divided, which object should be put in the knapsack if we want to have a maximum profit? So the solution itself can be represented as a tuple like this, where xi is equal to 1 if object I is put in the knapsack, or we choose the object to the knapsack, and it's 0 if we do not put the object to the knapsack. So 0, 1 here means we either take an object or we do not take the object. Mathematical model for 0-1 knapsack problem is we want to maximize the total profit we have from what we choose, and with constraint that the total weight of what we choose is not larger than the maximum capacity of the knapsack. If we use exhaustive search for 0-1 knapsack problem, you can see the video we have before about this. Each element xi in the tuple can have a value of 0 or 1. So each xi can have either 0 or 1. There are two possibilities for each xi. And we have n x's, so there are 2 to the n possible solutions. And to compute the total weight and the total profit of each possible solution, you can do it in big O(n) because you just need to sum up to n items, right? So the total time complexity of exhaustive search algorithm for this problem, 0-1 knapsack problem, is big O(n) times 2 to the n. We just need to multiply this and this. Now, let us consider greedy. There are 3 greedy methods that can be used to solve knapsack problem. There are greedy by profit, greedy by weight, and greedy by density. For greedy by profit, we think that I don't want to lose the item with largest profit. So here, we want to put the largest profit first to the knapsack. And then greedy by weight, have the thought that I want to put as many items as I can in the knapsack, with the thought that if I have a large number of items, then I will have the large profit. So here we choose an object with light weight first. And the last one is greedy by density. Density here means profit per weight. So we want to know the value of so here we consider the value of items regardless of their weight. So let us consider a stone. There is a regular one that has a profit of 5, but also the weight of 10, let's say. But we also have diamond that has a profit of 5, or let's say profit of 3, but the weight is only 1. Which one is more valuable? Of course, this one, right? We can get a profit through even if we only gain 1 kilo in the knapsack. So of course, this is more valuable. So this is what we consider as the set density. So we want to take items that are more valuable regardless of the weight. So here we want to choose object with large profit per weight unit first. And again, profit per weight unit can be computed like this. And the greedy components for zero and knapsack problem is like this. So for the candidate set, what are we choose in each step? We choose objects. So candidate set is the set of objects to be put in the knapsack. Next, solution function. How can we know that we already obtain a solution? We already obtained the solution if we don't have any candidate whose weight is less than the remaining capacity of the knapsack. Then that is the solution function. Next one, selection function. How can we choose a candidate to be put in the solution? Well, it depends on the methods we use. We can use greedy by profit so that we choose items with largest profit, or we can use greedy by weight, which means we always use weight items that has the least weight. And then we also can use greedy by density, which means that we will choose item that has the largest density first. And next, feasibility function. How if I already choose an object based on the selection function? Is there any constraint? Of course, we have the maximum capacity of the knapsack. So we need to check if we choose the candidate. It should not make the total weight of chosen objects larger than the capacity of the knapsack. That is the feasibility function. And the last one, objective function. What is our objective for this search? We want to maximize total profit of the chosen object. Let's go straight to the example. Here we have one knapsack of maximum capacity 16, and we have four objects that has their own weight and also profit. Now let us consider greedy by weight. Recall the selection function for greedy by weight is we want to choose the lightest item first. This is, we have the lightest item is item 2 and 4. You can choose anything between them. So let's say I choose the second item first, such that I have total weight of 5 and total profit of 15 from here. So I have the remaining capacity of 11. So the next one, I choose the next lightest item, which is obviously 5. So I can choose that item in the next step, such that I have a total weight of 10 and a total profit of 25. I still have 6 capacity left. So next I check the lightest object again, and this is the next one, which is still feasible. So I choose that object in the next step so that I have the total weight of 16 and also total profit of 37. I don't have any remaining capacity left, so of course I don't choose anything afterwards. So we have some solution that use greedy by weight method. And the next, greedy by profit. For greedy by profit, I don't want to lose items with largest profit, so I want to take it first. So here, this is the largest profit we have. So of course, that is the one that we choose first, such that we have the total weight of 10 and the total profit of 50. Now the largest profit is owned by the second item that has weight of 5, which is still feasible. So we choose it in the next step. Next, I only have one weight remaining, one unit weight remaining in the knapsack, and there's no feasible solution we have afterwards, so we don't choose anything. Next, greedy by density. Because we want to choose items based on density, we need to calculate the density first, of course. So here we choose the largest density first. This is the largest one. So we choose the third item first. And next, we still have six unit weight remaining. And the largest density the next largest density is the second item, which is still feasible. So we choose it in the next step. We only have one unit weight remaining, and there's no feasible item for that, so we don't choose anything afterwards. And if we find the solution by exhaustive search, which always give us the best solution, we can have this one as the best solution, which is the same with greedy by profit and also the greedy by density. So greedy algorithm for 0-1 knapsack, if we consider knapsack greedy by profit, we can have pseudocode like this, where at first we initialize the solution, and then assuming that the objects has been sorted uh, by profit, then we always check from the largest profit first, and we do iteration until either if all object has been checked or if we reach the K. We check the feasibility function, and then we update the total weight we have, and we return the final solution set. The time complexity of the greedy algorithm we just shown. In each step, we always choose the largest profit that can be chosen among all objects that has not been chosen. And to optimize the selection process, we can sort the object based on profit in descending order. And if we do not consider the sorting time, the complexity of greedy by profit algorithm for this problem is big O n, because you only need to check the feasibility functions for all objects we have. For the effectiveness itself, actually for 0-1 Knapsack problem, the greedy algorithm is not always accurate. The effective is not really good because we can have the solutions that is not the best solution. For example, it's like this: if we have knapsack with maximum capacity of 100 and also 6 objects with these properties, we can have these solutions by greedy, but actually if we use exhaustive search, we can have this best solution, which is larger total profit. So obviously greedy here does not give us the best solution. Now the next one is fractorial knapsack problem. Basically, this problem is very similar with what we have before, but here each object can be divided as needed. This means we can only take a part of an object. So in a tuple we have like before, in 0-1 knapsack problem, x can only be 0 or 1. But here we can have anything from 0 to 1. So the mathematical model for this is the same, but we just have different possibility for x. And it cannot be done by exhaustive search because we have infinite possible solution. X can be anything between 0 and 1, which is infinite. So we don't have 2 to the infinite, right? So this problem cannot be solved by exhaustive search. By greedy, like before, we can have three methods: profit, weight, and density. Same like before, greedy by profit means we choose object with large profit first. Greedy by weight means we choose object with lightweight first, and greedy by density means we choose object with large profit per weight unit first. And densities like before is P per W. Greedy components for Fractorial Knapsack problem is the same like 0-1 Knapsack problem as well, but here the selection function, yeah, we can choose only part of it. Now, example, let us consider the Fractorial Knapsack problem like this, where we have a knapsack with maximum capacity of 20, and we have three objects with these properties. Like before, we check the density of each object, but for weight, we choose the lightest item first, which is obviously 10. So we choose the third item first so that we have total weight of 10 and total profit of 15. We have maximum capacity of 20, so we have 10 remaining. We have 10 remaining. The next lightest object is the second one, which has 15 unit weight, but we only have 10 unit weight remaining. So here, because we can divide the item, we can only take 10 out of 15. So we can take to the third of the item, such that the total profit we have is 15, what we have before, plus 2 to the third times the profit of the second object, which is 31. And we have 20 as the total weight. We have reached the maximum capacity of the knapsack, so we do not choose another object again. By profit, we always choose the largest profit first, so we choose the first object first, but we only have two unit weight remaining. The next largest profit is owned by the second object, but it has 15 unit weight, while we only have two remaining, so we can only take 2 out of 15, like this. And we have reached the maximum capacity, so there's no object to choose again. For density, same as before, we always choose the largest density first, which is the second object, such that we have a total weight of 15, and we have 5 unit weight remaining to be put in the knapsack. The next largest density is owned by this third object, but we only have 5 left, and it has 10 unit weight. So we can take 5 out of 10 to gain 5 per 10 times 15 profit. So here we take only half of the third object to gain 7.5 profit. And because we have already reached the maximum capacity, we cannot choose another object, so that we have one our solution. And actually, this is indeed the best solution we can have for this problem. This is the pseudocode for greedy by density algorithm. So like before, we have initialization for the solution set. And for each object from the largest density, we check this feasibility function. If we can choose the whole object, we choose and we go to the next object. But if not, we only take part of it. And it means that we already have the maximum capacity, so that we can out of the loop and we got the solution. For the time complexity in each step, we choose the largest density that can be chosen. And to optimize the selection process, we can always sort the object based on density in descending order. If we do not consider the sorting time, Then the complexity of greedy by density for this problem is big O(n). And actually, greedy by density always can give us the best solution, the optimum solution we can have for this problem, for fractorial Knapsack problem. So for fractorial Knapsack problem, we can always choose greedy to solve the problem. Okay, that's all for this video. For the next video, we will talk about job scheduling with deadlines and also Huffman code. So thank you for watching and see you on the next video.